A penguin slides down an icy hill, dropping a height of 5 vertical meters. She then keeps sliding up another incline, this one only 4 meters. The ground is icy enough that friction on the penguin is negligible and can be ignored. Use conservation of energy to determine the penguin's speed at the top of the second incline. This practice problem will focus on the concepts of gravitational potential energy, kinetic energy, and of course, conservation of energy. Let's start by sketching the problem. We'll draw the first hill that's 5 meters, then it comes down, and then we'll draw the second hill that's 4 meters. And rather than drawing a penguin, we're just going to keep this simple, and this mass here will represent our penguin sliding initially in that direction. We should always start by adding in axes as well. So we've determined what the horizontal and vertical directions represent, their x and y, and also where the origin is. So I'm going to draw our axes down here so that this is the y direction and this is the x direction. And they're at the base of the hill at the x horizontal position that the penguin starts at. Now what we're interested in is the penguin's speed at the top of the second incline, so that's right here. The two positions that we know the most about are its initial position here. We're going to call this the initial spot, make an I for that. And then we want to know something about its final position here. And this is going to help us determine what type or types of energy the penguin has at those different locations by clearly stating what is the initial position, what is the final position. We know that any energy that the penguin starts with, plus or minus any work done on the penguin by non-conservative forces, is going to give us the penguin's final energy. So we need to consider now how much work is done by non-conservative forces, because we know a lot about those initial and final states, but we don't know anything about this. So let's first recall what is a non-conservative force. A non-conservative force depends not on position, but on path. Friction is a great example of a non-conservative force. Really, in Physics 1, the only conservative forces you deal with are the gravitational force and the spring force. We have gravity here. We don't have any springs. So any other forces are non-conservative forces. We said initially that friction is negligible, so there's no work done by friction. But what about the normal force? Anytime we have an object on a surface, there's a normal force on it. But if we look at the direction of the normal force on the penguin at any time, so for example, let's just choose a random time when it's partially down the hill. That normal force is always going to be perpendicular to the surface. So initially, it's this way, right? That's the direction of the normal force. As we go partially down the hill, it's again perpendicular. When it's at the top of the second incline, perpendicular. And the penguin's direction of motion, as I indicated here, is always perpendicular to that normal force. It's moving forwards. That means that no work is done by the normal force. Work depends on that force and that distance having some direction in common. If they're perpendicular to each other, no work is done. So what that means for us is that the work done by non-conservative forces on the penguin is 0. And that simplifies things. That means that we have an equation that's simply that our initial energy is equal to our final energy. Now let's talk about what type or types of energy the penguin has initially and finally. When the penguin is up here in its initial position, we have to ask questions about it in order to determine what types of energy it has. The first one, when we consider gravitational potential energy, asks, is the object we're considering, is the penguin raised up above y equals 0? And this is why it's important that we chose our axes initially, so we have that reference point. And we can see, yes, the penguin is above the origin, above y equals 0. So that means that we do indeed have some gravitational potential energy to begin with. Then we ask ourselves, is the penguin moving? Not initially, right? We're told that it's starting at the top of that hill motionless. and then it's sliding down. We're not told that it is in motion initially. That means there's no kinetic energy. Kinetic energy depends on energy of motion. And then we can consider, as I mentioned, is there any elastic potential energy from springs? There's no springs in this problem, so we can ignore that. Now let's look at this final state. Now it is still, we'll ask ourselves that question again, raised up above y equals 0. So it does have some gravitational potential energy. This is, again, why it's important to use subscripts well. I'm going to put an I there and an F there, representing this is its initial gravitational potential energy. This is its final gravitational potential energy. They are not necessarily the same number. In fact, we know they're not going to be the same because the penguin is at different heights at those two spots. Then we also have to ask, is the penguin moving? And yes, finally, the penguin is moving at this spot. So that means we also have kinetic energy. And this gives us our equation, that our initial energy is equal to our final energy. And our final energy has two terms. Our initial energy only has one term. Let's go ahead and fill in the equations that we know for potential energy and for kinetic energy. We know that potential energy is mgh, so our initial potential energy will be mghi to signify the initial height. And our final potential energy will be mghf, that hf being the final height. And we know that kinetic energy is 1/2 mv squared. Now, notice this is the variable that we want. This is the penguin's final speed. We know the initial height. We know the final height. We know g is just a constant, but we don't know the penguin's mass. That's not something we're given. However, notice that mass appears in every single term that we have, which means we can divide this entire equation by m, and the mass will cancel out. It doesn't actually have an effect on anything. That gives us a simpler equation that we know every single term in. Now that we've canceled out the masses, let's go ahead and plug in the actual numbers that we know. We know that initial height and we know g, and let's take a moment to notice that we are plugging in g as 9.81, not negative 9.81. Acceleration due to gravity is in the negative direction typically, but when we see g in a formula, we are talking about the constant g, which is a positive 9.81. It's not negative, so be careful there. Don't plug in negatives. So plugging everything in, we end up with the following equation, and we can solve for that v. We can solve for that final speed. And when we solve for that, we get the final answer that v is equal to 4.43 meters per second. Let's take this back and look at our initial problem and see if this seems reasonable. So again, with our initial problem, we have a penguin starting on an icy hill that's 5 meters high, slides down the hill, then goes up another incline rising about 4 meters. And our work with conservation of energy tells us that the penguin's speed at the top of that second hill is 4.43 meters per second. To put it in more familiar terms, this is not quite 10 miles an hour. This is fairly quick, but not at all unreasonable. There's nothing there that signifies that we definitely made some sort of error, like as if we'd gotten a speed that was negative, or very, very small, or very, very big. Let's also talk about sign for a moment. When we solved for velocity, we took a square root, which should tell us that the answer could be either positive or negative. But remember, all that conservation of energy equations are telling you is speed, though, so not actually velocity. The kinetic energy depends on an object's speed. It's never going to tell you anything about its direction. That has to be determined in some other manner. So we've just determined its speed, its magnitude of its velocity, nothing about its direction.